Good afternoon. Thank you everyone for joining us today. Today we're going to be discussing operational technology and industrial control systems cybersecurity and how AI is impacting it now and will impact it in the future. We'll also be discussing why it matters and why it should be addressed, and we'll be going over some mitigation strategies that you can take today to both proactively and reactively secure your AI. About us, Ulrich has been in cybersecurity for over 20 years. He got his PhD at Cambridge University in cybersecurity. This is his fourth time presenting here. He was also here last year, if anyone caught that presentation, on automated binary analysis for operational technology and industrial control systems. And he's been working in several areas such as AI and machine learning and binary analysis, vulnerability analysis, OT and ICS cybersecurity, 5G cybersecurity, and several other areas. I've also been working at object security, and I've worked in many areas such as AI and machine learning, binary analysis, automated component object detection on circuit boards, as well as several other projects, and I'm currently leading our Trusted AI project.
Right. Hi, everyone. So just to set the context, today is about AI in this OT ICS context. Of course, it's understood that there's many other areas in protecting OT ICS that people need to cover, including, like Jason just said, scanning your firmware, network scanning, other things, right? So we just want to kind of bring to your attention that this is something that's often forgotten, and thus our presentation here. And if anyone wants to listen to last year's, it's on YouTube, by the way. So if you can't find it, we made an alias this time round. Just email ai@objectsecurity.com and we'll send you whatever stuff you want, right? So yeah, with that, I'll click the button. CWE 1039 is one of the CWEs for machine learning. So there's a mouthful here that I'm not going to go into because we got it again on the next slide. So I can read it out quickly. It's automated recognition mechanism with inadequate detection or handling of adversarial input perturbations. Bit of a mouthful. I'd say the important part is it's quite intuitive. You put some input in an ML system and as an attacker, and it makes a bad or wrong decision, right? So that's actually a MITRE CWE in 1039 basically is the number. And there's some quotes here. Pretty much, they are very specific. It's about ML, and the bold part is an example they even have in the CWE, essentially an autonomous vehicle kind of making the wrong turn or wrong decision based on the computer vision system not being accurate, right? We'll go a lot into the kinds of attacks and mitigations later on. On the bottom half of the slide, you can see how this pertains to the context of OT ICS. It obviously pertains to other systems too, but that's today's focus. And the key piece, one of the key pieces is that there's physical and cyber-physical damage that can happen that's potentially substantial, right? So you're looking at this as especially sensor networks, autonomous vehicles, smart cities, smart power, whatever is coming up. That's all use cases that already have things like computer vision in there or other machine learning things and are vulnerable, right? So there's reputational harm. There's the whole laundry list of things that could go wrong that you guys as cybersecurity people know. But cyber-physical is a big one, right? So we have in red here kind of our interpretation of the same thing that's at the top. Wrong security or safety decisions would be one of the outcomes, right? That negative outcomes of an attack of an ML system. We got an extreme example there causing a nuclear meltdown. That's maybe a little extreme, but you could foresee that if ML is used to kind of keep that in place. I wouldn't recommend it, but you have it for transport already. Everyone knows that, seen the news. We got real world case studies coming later too. Mitigations we will cover. They're basically in two categories. One is detection and one is hardening mitigation, and we'll cover both of those. All right, let me see that I get to the next slide. There we go. Here's a picture to go with this. You see two things that for us look the same, two stop signs. However, one has been slightly modified with some few pixel changes here and there, and would, for example, by an attacker then be, could be with a sticker, or it could be in the training data, be modified such that the car thinks it's a slow sign instead of a stop sign. We'll show you more about that later also, but that's the backdrop to the CWE 1039, right? With that, I want to kind of mention that there is an emerging, for lack of a better term, guidance and compliance landscape. So people are working hard in many working groups to tackle all this. The fact that this came upon us as cyber people, yet another mechanism that came out of the woodworks real hard, and we somehow need to make sure that it stays secure, right? So MITRE is one. They have Atlas that used to be called Threat Matrix with a bunch of mouthful title, right? It's essentially threats, tactics, etc., kind of categorization based on the attack framework. I guess I can go into detail in the Q&A. We have a bunch of stuff here. This is more for handouts. When we have a lot of details here, we're not going to won't bore you with each of the bullets, but you can map essentially all of this Atlas stuff into 1039, CWE 1039 related things. And yeah, there will be more coming. With that said, we are involved in some of those working groups like MITRE, CISA, ISC, and CS2AI. I read that, by the way, from the paper, and don't make me say it again. It's a mouthful, and that's only some of them. So we have a nice acronym soup of agencies and interest groups working on this. With that, I'm going to race through a bunch of those, and you will have to look at that. This is coming down in the near future. So sticking the head in the sand or figuring out we do it later, like we've kind of done in cybersecurity because things were slowly emerging. This is not one of them, right? It's already coming at us at breakneck speed. So this is ISA IEC 62443. It's an industrial automation and control systems security standard, that a certification framework. And what we've done on the next couple of slides is we'll take controls from things like this 62443 and map them, that's on the right side, map them to our interpretation, how you would map them to 1039, right? Because you can't wait for the controls to specifically say AI or something. AI is just a mechanism like any other mechanism that we as cyber people have to deal with, right? So you kind of, stuff gets grandfathered right into existing compliance at times, right? And again, it's rapidly emerging. So with that, moving on to 853, everyone knows that. There are some controls that we mapped, won't go into too much detail, but these do relate, and NIST's obviously been very active in publishing numerous good things about how to deal with AI risks. So again, the right side is our mapping, and it's kind of handout material, so you guys can download that from the website afterwards, or email us, like I said, ai@objectsecurity.com, and we'll send it to you. Then we got 882, mapping to CWE 1039, so that's the ICS security guideline from NIST, security and privacy, in fact. There's also a bunch of controls here, like flaw remediation. These are all very broad categories. And actually, the AI systems, including the ones that would have CWE 1039, they fall under those, right? So this is kind of important. So I would say, state the obvious here, sticking the head in the sand is not really an option right now because stuff is emerging so rapidly. And with that, there's a good document from NIST, the AI RMF version 1.0 that was released recently. Talked to the guy that's involved in this at a talk earlier this week here at RSA, and he was saying they're starting working on the 2.0. So there's more coming, and we mapped again controls into how that would look for CWE 1039 as an example here, right? There are others. Unfortunately, these slides had to be submitted like a month early, so we had to cut off at some point. But there's the OWASP top 10 ML that they ML risks that they published. There's numerous more. I think all the AI talks had that issue that you're racing against rapidly evolving space. But if you are compliance driven, at least in some form, and most people will be, you have to keep an eye on this. This is not something where you can wait for a long time. right? So I just want to kind of bring that to your attention. I know it's a racing through a lot of different things here, but that's it. So I guess with that, over to Jason. We're tag teaming this today.
Great. Now we'll be going through the role of trusted AI and defense systems in the protection of operational technology and industrial control system environments. So more and more, we're seeing more and more advancements in AI innovation and the technology that's now enabling it to run on embedded devices. So we've seen advancements to hardware acceleration, such as with edge and fog devices that can analyze large volumes of data and also aggregate large volumes of data at the edge. We've seen advancements to hardware such as FPGAs, CPUs, TPUs, GPUs, and other processing technology. This has led to a proliferation of embedded devices in smart grid and industrial settings. Emerging and enhanced architecture specifically for AI, such as convolutional neural networks, large language models, transformers, transfer learning, and others. And this has led to more kind of complex and in-depth AI. And additionally, while we've seen these models become more and more complex, at the same time there's been technology like ONNX and OpenVINO that have allowed you to both compile and compress your models to be able to run on embedded architectures like ARM. Lastly, OT and ICS is increasingly connected to internet for remote accessing and monitoring. So in these situations, you may need some sort of network analysis monitoring tool. In other cases, because of these advancements that we've been seeing, AI is also becoming increasingly deployed directly to the embedded device for lower latency or for quicker decision making. And in these situations, the models could then be prone to being reverse engineered, where then the proprietary model and data could be stolen. From our experience working in OT and industrial control systems, there are many different use cases that we've personally come across, and these are kind of just some examples that we put here, and there's a lot of text, so this will be posted online if anyone wants to read it in depth later, but I'm just going to quickly run through some of the main ones here. It's being used in cybersecurity and intrusion detection systems for detecting and preventing real-time attacks on OT and ICS. It's being used in automated decision making, like with robots and drones and vehicles. It's also being used in edge and embedded AI for analyzing sensor data at the edge. It's being used with supply chain risk analysis, also with logistics and maintenance operations and planning. And lastly, it's used with predictive maintenance, so predicting whether a part is ready to be retired or whether it is more likely to break or have some issue with it. Now we're going to be going into some of the types of attacks, so we'll jump right into that. The first example of an attack here is one of the more popular types of attacks, which is an attack on the inference of the model, which is called an evasion attack. These kind of do as the name says, that they're evading being detected by the system. So in our example here, we're showing a computer vision model at a nuclear power plant. And here the computer vision model might be doing a variety of things. It might be detecting if there's some physical anomaly with one or more of the devices. It might be detecting if there's a fire or if there's smoke, or maybe the guy that's there that kind of looks like Mario, maybe he's an intruder that's not supposed to be there, and he's supposed to be detected by the system, and then security would come and go get him out of there. So how these attacks work, it's very similar to the stop sign example that we showed earlier, where there's an original image that we have on the left side. In the image in the middle, we have a perturbed image. And so that's the image that has the slight modifications made to it that then trick the system into making the wrong decision. And We tried to highlight those on the right side. If you can see the little dots on the image, those were the specific pixels that were changed. And they were changed in a very specific way that attacked the model's kind of patterns that it's recognizing in the system. So for a human, when we look at these two images look exactly the same, and that's kind of what makes it very difficult to then later on go through and you're trying to figure out why did the system make the wrong decision and break. For us, it's kind of, we don't really see the difference between these two images. And this could have pretty severe consequences in an operational technology environment where if there's a fire or if there's some physical anomaly, then it could go undetected. Or if a human would be slower to actually step in and fix it, then kind of the automated fixes for that would take place much later. Another type of attack is a poisoning attack, and rather than attacking during inference, which could actually happen as a result of these attacks, poisoning attacks attack the training data by injecting malicious data into the training data. And so we have an example here. It could be used in many different use cases by the attacker. The attacker may be wanting to inject a backdoor into the training data that they can then use later during inference. They could use it to cause biases, or in some cases, biases and discrimination. It could also be to just lower the accuracy and confidence of the model. In our example here, it's similar to the previous slide, but we put a pattern in the corner of the image that you can kind of see in the bottom right of the diff image. And so now that's kind of used as a backdoor, and then during inference, the attacker now can use that same backdoor to then attack the model and then take control of it. A patch attack is a type of attack that's kind of it's in a greater category of attacks that attack the physical environment. And so this could be stickers, or it could be a poster, or glasses that can get around getting detected by face recognition software. In this case, there's a specific type of attack called a patch attack, where you can train a machine learning model if you have the original weights in the original model that you're attacking, and you can generate a very specific image, which is what's shown in the bottom left there, that can then target a specific class and then cause it to misclassify to that class. Due to time, there's so many types of attacks that are out there, but we could only have time for a few of these. But if anyone's interested in any of the other ones, we'd be happy to discuss them after the talk. To quickly run through some of the other ones, there's other types of attacks on computer vision. We mostly talked about classifiers. There's also attacks on object detection models, where you can cause the model to mislabel or to falsify or change different labels in an image or other. There's attacks on natural language processing models, which could be phishing detection or malware detection. What we typically see with natural language processing attacks are that they swap out letters or intentionally introduce typos, and so you'll see they add in abnormal characters to kind of cause the model to make the wrong decision. And there's also attacks on signal processing models. One thing that's important to note is this isn't all theory. We're already seeing real-world case studies of this actually happening. For example, a lab found that 3 small stickers caused Tesla to swerve into the wrong lane. And so through trial and error on the physical environment, they were able to figure out a pattern that they could put on the road that would make the model think that it needs to make a lane change and then swerve off into the wrong lane. Hackers also claim to be able to trick Apple's Face ID using a 3D printed mask. And using this printed mask that they made, they were able to get into an iPhone that wasn't their own and unlock it. Similar to the Tesla attack, traffic cones confused a Waymo self-driving car and caused a traffic jam where it thought that the cones were an object in the road that it couldn't go past, and it also couldn't go around, and it ended up causing a big big traffic jam. And also, they're used to evade phishing and malware detection. And we've seen there's actually one CVE that's related to this where they were able to trick it into giving it information and giving up its proprietary data, and they were able to make a copycat model of that model.
All right. So now some what-if scenarios. Very briefly, we covered some real-world ones, but there's obviously countless more. So just as an example of what could happen in these OT ICS environments, you're looking at something like delivery drones or any other autonomous vehicles where physical damage could be caused, reputational damage could be caused, sabotage is another kind of a reason for attacking, or theft, plain theft, like if this is a delivery drone, for example, stealing the packages is one of them. These delivery drones are already in use. It's just not your pizza that's coming yet, but it's other things where they're already being used, right? So I won't go into the gray boxes specifically because we've already covered a lot of those attacks. But you know, when you add those up, you can achieve all those things potentially. So there's a lot of attack surface and reasons for attackers to attack those kind of systems, right? Another example where this could happen is a chemical plant where, for example, sensors on the edge would mix chemicals or detect chemicals, etc., or detect heat or other things, right, and make decisions on that. So analyzing sensor data, and attacks can have serious consequences on the physical environment and consumer safety. Think of incorrectly mixed medicines, right, or whole batches of some chemical thing being wasted because of some attack where it didn't detect the composition correctly, or it could be something like this fire there that we have. So this is just an example, but you see in these kind of manufacturing environments, this could be really serious. Here you got automotive manufacturing. It's kind of interesting because if you haven't lived under a rock, you've probably seen the videos of these car factories with all the robot hands doing like 99% of the car, right? A lot of these use ML. Some of them even use reinforcement learning, so they have reinforcement learning cycles. Threat actors could introduce malicious data into the ML, or could be evading it in other ways. I think interesting is also corporate espionage. I got that on the third bullet here, where the model itself and what it predicts is essentially like a data leakage of, say, your operations and your operational efficiency. So a competitor might be interested in those kind of things. And then obviously the usual laundry list of financial loss with faulty product, reputation loss, physical harm, brand reputation, etc. Right? So pretty substantial. So with the military, it's worth pointing out that DoD is one of our key customers at Object Security. Incidentally, we're doing a project on trusted AI with them, which we can't really go into detail here, but again, you can email us at ai@objectsecurity.com and we'll send you what we can. I would say when you look at this, it's kind of an interesting one. So they're obviously always a bigger attack target than anyone else. And they're using a lot of computer vision and other ML for ISTAR and other things on UAVs, for example, to detect, I don't know, adversarial tanks and movement of people, etc. Right? So here you see a picture of a tank in camouflage where it would evade detection, right? Because they didn't train it with this kind of, whatever you call it, jacket, I guess. If you do that not on the physical evasion end, but you do it on the poisoning end, and you already put some training data in where, for example, it will exclude you as a person detected based on a sticker on the helmet, and then all the adversaries that want to be not seen would just have that sticker until somebody finds out. That would be an attack that could happen, you know. So there's a lot that could go wrong. I would say still there is. These are all OT ICS kind of environments. The way you depending on how you define it, like a vehicle with some technology in it, doing stuff like a UAV, right? It is essentially OT, and these things have been using ML extensively everywhere, right? And like I said, I will just reiterate because it's important, is we're presenting the AI side of OT, ICS, cybersecurity here, but there's more to it. This is one often forgotten aspect, so don't forget your firmware scans. Like I said, last year's RSA presentation is one thing. Don't forget your network scans on these things, et cetera, et cetera. It's just cyber hygiene, basically. And with that, I think we're over to Jason for, now that you know how bad it is, what are we going to do about it? What are you going to do about it, rather? Not me, it's your problem.
Now is the fun part with the mitigations and also defense methods. And we kind of created a table of contents here of all of the different types of defense methods. So I'll try to run through these quickly, and if anyone wants to discuss them in more detail, we can after this. Adversarial attack generation, testing your machine learning models against known types of attacks like FGSM, BIM, and Carlini and Wagner. Formal verification of testing properties to make sure that your model is acting within specific boundaries. Noise detection and removal for removing potential noise of an adversarial attack over, for example, an image. Post-processing and pre-processing your data to ensure that it's safe from an adversarial attack. Model deployment, where you're checking your model before it ends up getting deployed. And then model monitoring, where you're continuously monitoring your model and its behavior and susceptibility to attacks. To go into detail just with one of them, what we show here on this slide is noise detection and removal, where we have the stop sign again with 3 examples. On the left, we have the original image, and then in the middle, we have image where we had noise that was generated over it. Then we ran an algorithm that removed noise from the image, and that's on the right image. The left image correctly identified as a stop sign, the middle image classified as a slow sign, and then the right image again was classified as a stop sign. So the denoising algorithm correctly mitigated that noise that was placed over the image. Adversarial defense, observability of model behavior. Another really important aspect of understanding what's going on with your model, which is typically trained as a black box and has very little visibility into it, is understanding how it's making its decisions and how different features impact those decisions. There's visualizing and detailing activations of neurons in a CNN. This would be creating different visualizations to then view what features were most important in its decision making. Monitoring inputs to the model and how it affects the output. Model agnostic explanations, and there's different frameworks that exist for that, like LIME and CHAP. And identifying bias and discrimination by checking sensitive attributes. And in this case, you're checking for data that might be not balanced or might contain data that would cause biases. And it's very similar also with adversarial attacks, where your data isn't balanced or doesn't contain adversarial samples and then would be biased and not robust against those types of attacks. There are a lot of inherent issues in detecting adversarial attacks that we've come across. The first one is that all models are vulnerable. The second is that accuracy and robustness have been shown to have trade-offs typically, where if you try to train your model to be more robust, you end up having a trade-off and giving up some of your accuracy. And so, on the other hand, more robustness in defenses leads to it being harder to attack and also easier to defend. One issue is that a one-time attack on an operational technology and an industrial control system can have severe consequences. So compared to other areas of adversarial attacks on AI, it could be much more severe in an operational technology environment. Security personnel currently do not consider AI and machine learning as a threat, and so they're not really monitoring it, and they're not considering the attack surface. Also, attacks may not leave traces or signatures for detection. And so even if you know that your model may have been attacked, it may be hard to figure out where it was attacked, and for example, in computer vision, which images were attacked. The state of the art is also heavily geared towards proactive mitigation, so that adversarial defense and including adversarial samples and training data, they're not really focused on reactive and detecting attacks. And lastly, there's no standardized scoring mechanism for when you should know that your model is secure enough and robust enough to be able to deploy it. In summary, to scan for 1039, you can proactively test your model, you can reactively protect your model, detect boundary violations using formal verification, model explainability and understanding the underlying decision-making of the model and getting explanations into what features and what decisions made it make its decision, and also including continuous monitoring and machine learning operations pipelines. Here we have an example of explainability in the form of a visualization where we're analyzing what features the model looked at during inference, and we're highlighting that as the stop sign. If it didn't highlight the stop sign, then that would probably be something that would be a cause for concern, where maybe there was some sort of poison or backdoor or issue that caused the model to look at the wrong feature. Here we have proactively securing AI and machine learning, so what measures can be taken. Again, we kind of have a whole list here, so I'll try to go through these quickly, and if anyone's interested in any of these in more detail, this has been a focus of my work at Object Security, and I'd be happy to talk about them. We have robust optimization, where we're taking specific measures to make sure that the model is robust before we train it. Minimizing the model's exposure to attackers, so limiting who has access to the model and its API, or other ways to make inference, or what data they have access to and how much of that data they have access to. Adversarial training, where we're including adversarial samples in our training for specific types of attacks to make it then more robust against those attacks. There's defensive distillation, where we're training a second model that then verifies the original model and then detects if there's any violations or differences. And we can watermark the data or use blockchain to ensure that the data doesn't change over time. And then lastly, there's specific ways that you can compress a model to then make it more robust and optimize it for robustness against adversarial attacks. In terms of reactive measures that can be taken, there's adversarial detection, where we're monitoring and detecting attacks either before or after inference, and then determining if what was given was an adversarial attack. Noise removal, which we showed you, pre-processing the data to sanitize it and possibly subsample that data and ensure that it doesn't have an attack. Even after the model's been trained, you can still fine-tune the model and improve it over time. You can detect out-of-distribution data, which we're showing in the image here, where we can visualize a specific cluster of samples that we gave for inference, and then determine if that cluster looks like it has a vulnerability. And then lastly, we can disable access and fortify the system and block off access from someone who might be introducing an adversarial attack. There are many initiatives, some of which we're a part of. There's ISA Secure that doesn't currently include AI as part of its certification program. However, we think that in the near future, AI will be a significant part of it. There's also ICS for ICS training that provides hands-on training to ICS professionals, and they're also not currently considering AI as part of their training, but we think as AI continues to advance and then the attacks and mitigations also continue to advance, that they're going to need to include it as part of their training. And lastly, based on our own experiences, we have our own suggestions here. First is a database of proven vulnerable models. This currently doesn't exist for AI and machine learning. It does exist in CVEs, but there's only one CVE currently that actually relates to adversarial attacks in AI and machine learning. Include AI and machine learning trust analysis and SIEM solutions for continuous monitoring. Standardizing the scoring systems where we can figure out how robust a model needs to be and what metrics need to be obtained in order to ensure that the model is safe enough to deploy in critical infrastructure. Lifecycle management, understanding at what points in the life cycle that the model should be analyzed and monitored, and when it should also be retired after, for example, there's changes in the data that's being inputted. And lastly, integrate AI vulnerabilities into larger operational technology and industrial control system risk management frameworks, like some of the ones that we talked about earlier that we think that will soon cover AI and machine learning. Now I'll hand it over to Ulrich for some takeaways.
Yeah, we got pretty beefy takeaways. By the way, if anyone wants to talk about these working group efforts, we got Susan over there who's working at Object Security too, and she's you can talk to her afterwards about that also. There's a lot of efforts. All right, with the takeaways, so the first one, machine learning models are susceptible to attacks, and they always are unless you put defenses in, right? That's just the nature of it. There's really not, without that, there's no theoretical way for you to prove that it's secure or not, or can be thwarted or whatever either, right? And I kind of want to dwell on this for a second, because there's been talks throughout this RSA about what's going to come down the pike, and I think where it's going to go is that whatever you build in AI today or use today, it's going to kind of be grandfathered into whatever guidance or compliance or regimes are going to be there in future. The same way, if you're a CISO, you can't stick your head in the sand about some old device hanging on your network that was bought before you became the CISO or before there was a standard. It just applies at that point. So a lot of stuff will just apply, and you got to kind of preempt that roadmap. I can go on about that all day, why that's important, but it's the detection and the mitigation piece there, right? So that's the first one. Second, these attacks pose serious risks to OT, ICS, and critical infrastructure. So that's because critical decisions are made by those systems that are safety critical often, you know, that's kind of the nature of many of those. And the impact, the damage, so to say, could be significant. I just kind of can't stress that enough. Yeah, and then the third one is OT, ICS are susceptible to a wider range of attacks. I kind of want to throw in again, there are many attacks beyond AI. Yeah, we spent a lot of time on binary analysis. We actually, like I mentioned our talk last year, and we have a product there too, and it's just that little piece is a gigantic effort. So I think where we are in OT, ICS is we're not, as an industry, nearly as mature as with IT. In fact, very immature when it comes to cybersecurity. So we really have to look at that, and it's a double whammy that we're now dealing with those ML things in this context also, right? So it's substantial that I would definitely urge people to look into that this is likely going to come sooner than later on your plate if you're in cybersecurity, right? Which everyone here is. So the reasons why they're susceptible to a wider range of attacks with or without AI is because they're often physically exposed, right? They're often even exposed to an attacker physically, right? Like a smart city system. Anyone can walk up to a smart light thing or anything else, right? They're often autonomous, not just vehicles, but other things, right? So at that point, there's no human in the loop. That's nice, but if you have a problem with the human factor in cybersecurity, but it's also pretty bad because it lets the attacker do a bunch of stuff, right? And they're often badly maintained. I won't go into the whole legacy story unless we got time at the end. AI/ML security needs to be proactively planned and emphasized. This is where you would need to create a roadmap at least, and don't play catch up later. This is going to come down faster than we like, I think. in previous cycles like privacy, it's taken people like 20 years to catch up. Here I think we're seeing already at the nascent stage of this explosion of AI that a bunch of governments and NIST and everyone else, they're already, and the EU is doing an AI, they have a thing for an AI, what's it called? AI, it's like an AI regulation essentially, I've forgotten the name right now, but this is going to be years in the making probably before it's through. But we're way ahead of the curve when it comes to regulating this stuff. So you got to kind of keep an eye on this. The fifth one, defense need to occur at all stages of AI, ML development for OT, ICS. So this is not just DevOps or DevSecOps if you're like a manufacturer. This is also for the consumer, the buyer, and the maintainer, the facility managers, all of these people. So develop, deploy, operate, maintain, etc. It's pretty important to look at it from that sort of broad picture. And with that, we have the obligatory last slide here with a bunch of how you apply it. Pass that over to Jason.
The first step of how you can go back and apply this at your organization would be to discuss with your team how you're currently managing AI vulnerability analysis, understanding if you're managing it or what you're currently doing. Are you considering the attack surface? And then discuss with your team what you could possibly implement today or in the upcoming months and years to be proactive about this. The second thing is identify attack vectors that AI and ML adds to existing OT and ICS systems. So these could be some of the ones that we discussed earlier: attacks on the training data, attacks on the model itself, attacks during inference or in the physical environment. The third one, define clear metrics and requirements that models need to meet before deployment. This would be the scoring mechanisms, what metrics need to be met in order to safely and properly deploy these models. The fourth one, use existing tools for both cybersecurity of the system and AI and machine learning robustness. There's a wide variety of open source tools that are out there, as well as the tools that we're working on that allow you to ensure that your model is robust and test them against a variety of attacks. Continuously monitor your systems for any new threats and ensure that your team is aware of any emerging attack techniques. We've already seen that there's hundreds of papers being posted every single month in the AI Trust community about adversarial attacks, more on the attack side than the mitigation side. And so we're expecting that in 2 months from now, 6 months from now, a year from now, it's going to totally change again. And so it's not just enough to know what the attack and the threats that are available now, but you have to keep up with it and understand new and emerging threats. Promote regular training on best practices for securing AI on OT and ICS systems. So currently, like we said earlier, cybersecurity professionals aren't really considering the AI threat landscape. And so they also need to understand what mitigations that they can take or what mitigations they can tell their AI teams that they need to make. And lastly, regularly review and update AI and machine learning security policies within critical infrastructure. These would be the NIST frameworks and the MITRE frameworks that we discussed, as well as others, and your internal compliance policies, and ensuring that they meet guidelines and emerging threats.
Yeah, and I think one bullet that should have gone on this is that when the law hits, everything's going to apply. I think that's something related to the last bullet that was kind of mentioned many times in those AI legal presentations earlier this week, and we've talked to our own attorneys about this. So I think the takeaway would be to start documenting, say, your models for bias. Use explainability to start documenting. Document the process that you followed, or what images were used, or whatever it is. Did you get consent for the images, etc.? I don't have all the answers, but think of for lack of a better term, an SBOM for an AI model. We don't have that, and that's okay. But the thing is, whatever you build before the law hits, the law will still apply to. So you might as well get ready for this. And that's, I think, relates to the last bullet. And with that, I think we can open it for questions, right? We got 5 minutes plus. I think we're the last guys, so we got until we get dragged off by RSA from the stage. So if you have any questions, please, or any comments, there's the mic, and that's it from us. Thank you. All right. Oh.
So thank you for the interesting presentation. I was a little bit concerned though about a couple of the mitigation techniques that you proposed related to data sanitization and the ability to distinguish out of distribution data in your training samples. These are good suggestions. However, theory says that you cannot defy gravity. There is a theoretical result that says that you cannot distinguish out of distribution data as long as the two distributions overlap, even a little bit. So you cannot define an algorithm that could do that. So my point is that we need to sort of keep updating with the latest advances in theory and draw limitations of those mitigation techniques that we promote to the community, because they are not perfect.
Yeah, it's a valid comment. I would say when it comes to mitigations, also for the people, Jason mentioned there's a lot of publications. I think what we're seeing of the 1,000 plus, well over 1,000 publications, it's probably a factor of 10 on the adversarial attack size that academics work on, and 10%, if that, maybe 5% are on mitigation. So that's the more nascent stage. But I think if you know enough about your data, you can't build a general purpose algorithm to debias your data or something. But if you know enough about the data and everyone's clear on it, you can build something to catch it. Do you have anything to add to this?
I think you covered it well.
I think this is pretty much our stance. There's probably not going to be a general purpose product that just makes sure you don't have bias in your data, because the question is, what does that mean, right? So I think there's a lot to that. The whole with the overlapping, yeah, I think it's evolving fast. Let me just say that data scientists will need to just work with this on a case-by-case basis, in my opinion, until we have more, right? Yeah, so that's pretty much, I think we just want to make sure that people understand this is for OT ICS, right? So we're having significant cyber-physical challenges. I just want to rub that in again, right? So a car, an autonomous car, or a delivery drone, these are the kind of things that are going to be societal risks, right? More than maybe some financial loss due to some model being wrong somewhere, right? So that's the sort of the backdrop to this presentation. Not to do FUD here or something, but I think it's substantial. All right, thank you.